So good day everyone. I am Adrian Morio and my partner Angel Ferrante will explore about one of the branches of advanced ceramics called bioceramics, where it can be applied in the biomedical field. But first, we will have a quick discussion on what is advanced ceramics. So, what is advanced ceramics? Advanced ceramics refers to a class of high-performance ceramic material that exhibit exceptional properties and characteristics. Unlike traditional ceramics, advanced ceramics are engineered to possess specific attributes such as superior strength, hardness, wear resistance, thermal stability, electrical insulation, and chemical inertness. These materials are designed for specialized application that require advanced performance in demanding environment. Advanced ceramics are typically composed of non-metallic or inorganic material, including oxides, nitrides, carbides, and silicates. Examples of advanced ceramic material include alumina or aluminum oxide, zirconia, silicon carbide, silicon nitride, and boron nitride, among others. The unique properties of advanced ceramics makes them highly desirable in various industries, including aerospace, automotive, electronics, and biomedical field. So in this video, we are going to start to talk about the application of advanced ceramics in biomedical field.
What are bioceramics? Bioceramics is a class of materials that gained an increasing amount of importance in the fields of medicine and healthcare. It has three classifications: bio-inert, bioactive, and bioresorbable. The main differences between these three types of ceramics lie in the reactivity with biological systems and their fate within the body. Bio-inert ceramics are materials that exhibit minimal reactivity or interactions with living tissues when implanted. These ceramics are designed to resist degradation and maintain their physical and mechanical properties over time without eliciting a significant immune response. Examples of bio-inert ceramics include alumina and zirconia. They are commonly used in orthopedic and dental applications, such as joint replacements and dental implants, where long-term stability and compatibility with the body are crucial. Bioactive ceramics actively interact with biological systems and promote a desirable response at the material-tissue interface. These ceramics have the ability to bond with surrounding tissues and stimulate the formation of a strong and stable interface. Examples of bioactive ceramics include hydroxyapatite and certain calcium phosphate ceramics. When implanted, these ceramics can promote bone growth and osseointegration, making them suitable for bone grafts, bone fillers, and coatings and implants. Bioactive ceramics provide a favorable environment for tissue regeneration and integration by enhancing cell attachment and promoting new tissue growth. Bioresorbable ceramics, also known as biodegradable or resorbable ceramics, are designed to gradually degrade and be absorbed by the body over time. These ceramics are typically made from materials such as tricalcium phosphate or calcium sulfate. When implanted, they provide temporary structural support or act as scaffolds for tissue regeneration. As the ceramic gradually degrades, new tissue grows to replace the material, and eventually, the ceramic is completely resorbed by the body. Bioresorbable ceramics are commonly used in applications where temporary support is needed, such as in bone defect fillers, scaffolds for tissue engineering, and drug delivery systems. Bio-inert ceramics can be synthesized by physical and chemical methods. Physical methods include flame spray, mechanical ball milling, and laser ablation technique. The chemical methods such as sol gel, co-precipitation, hydrothermal, combustion, and vapor phase reaction. For the bioactive ceramics, we have hydroxyapatite. Several methods have been developed to produce synthetic hydroxyapatite with the precise control of its structures. We have dry methods, wet method, high temperature processes, synthesis from biogenic sources, and combination procedures. Briefly, the dry methods do not require the use of a solvent. In the solid-state synthesis, the calcium and phosphate containing initial reactants are mixed and calcined at high temperature around 1000 degrees Celsius for a specified time. During mechanochemical synthesis, the precursor materials are ground and mechanical energy is used to promote chemical reactions and structural changes. The wet methods are based on the reactions in the solution carried out at different temperatures, using different solvents and applying diverse chemicals and apparatus. Different additives are often used to control precipitation. Chemical precipitation is a simple method of hydroxyapatite production using various calcium and phosphorus precursors. Properties obtained hydroxyapatite depend upon the synthesis method, example, the calcium phosphate ratio, temperature and pH, as well as ripening time. During the solidal processes, a sol, which is colloidal suspension of solid particles, is transformed into the 3D network of solid phase. In this method, precursors, generally alkali, are mixed, then aged, gelated, dried, and calcinated to remove organic residues. Using hydrolysis method, hydroxyapatite is obtained by transformation of different calcium phosphate phases, mainly in an aqueous solution. Hydrothermal synthesis can be described as a chemical precipitation taking place at higher temperature. In this method, organic modifiers are often used to control morphology and structure of the obtained crystals. Sonochemical methods allow formation of uniform particles, which always yield nano-sized products resulting from the chemical reactions occurring in the presence of ultrasound radiation. The hydroxyapatite synthesis in emulsion inhibits the formation of the agglomerates and allows control of the size and morphology of the obtained particles. The emulsion synthesis can be carried out in water and oil emulsion, oil and water emulsion, and water and oil and water double emulsion using surfactants of different natures. And the processes carried out at high temperature, the rest temperature is used to completely or partially burn the precursors. Combustion is a single-step process producing a product of high purity. It requires fuels such as urea, which after ignition at quite low temperature require energy supply for completion of the combustion reaction. In the pyrolysis processes, the particles are formed from reactants in a gas phase generated by physical evaporation of liquid precursors without the addition of any fuel. The precursor solution is sprayed into a flame or hot zone of an electric furnace by means of ultrasonic spray generator. As for the hydroxyapatite synthesis based on biogenic sources, they can be put into four groups. The first one of the biogenic reactants from the eggshells and exoskeletons of marine organisms are used. For example, calcia produced from eggshell via calcination at high temperature is hydrated and reacts with phosphoric acid to precipitate. The calcium and phosphate molar ratio is mainly maintained at 1.67. The second method is the synthesis in the presence of naturally derived biomolecules. There is also the synthesis method in which biomembranes are used. Another way of hydroxyapatite production is extraction of hydroxyapatite from bones, example bovine cortical bone, and its thermal treatment at high temperature is around 800 degrees Celsius in order to obtain crystalline white hydroxyapatite powder, which is then milled to provide particles of needed size. Moreover, it is also possible to combine two or more of the above described methods in order to obtain hydroxyapatite with better properties, such as hydrothermal hydrolysis. Apart from the combined procedures, it is also possible to modify the described method by introducing new procedures. One of such well-known modifications is the applications of microwave radiation to activate the reaction. The microwave heating can be used to generate heat inside the samples instead of the external source, thus reducing the reaction time and increasing the rate of nucleation and growth. Overall, the development of advanced ceramics continues to push the boundaries of material science and engineering. Researchers are exploring new compositions, processing techniques, and applications to enhance their properties and broaden their potential uses. With their remarkable combination of strengths, durability, and specialized properties, advanced ceramics have become indispensable in modern technology and manufacturing, driving innovation and enabling breakthroughs in various fields. Hi, my name is Angel Ferrante, a ceramic engineering student of MSU-IIT. As a ceramic engineering student coming from a humble background, I understand the challenges and financial constraints that can arise while pursuing higher education. Despite the difficulties, I'm determined to overcome them and make the most of my academic. Growing up in a poor family, I had limited resources and financial support. However, my passion for ceramics and my determination to improve my family's circumstances pushed me to pursue a degree in ceramic engineering. I realized that education was my pathway to a better future, and I wanted to break the cycle of poverty. While studying ceramic engineering, I have encountered various hurdles due to financial constraints. I was fortunate enough to be admitted in MSU-IIT, where they not only offer standard education, but also free education. But during the pandemic, things have become more challenging for me. I wasn't able to keep up with everyone. Thus, I was forced to stop. Despite that, I remain passionate about ceramic engineering. I find joy in experimenting with different types of clay, glazes, and kiln designs. The field of ceramics offers endless possibilities for innovation, whether it's developing advanced ceramic materials for industrial applications or creating beautiful artistic pieces. My ultimate goal is to complete my degree in ceramic engineering and utilize my knowledge to contribute to the field. I hope to secure a job in a ceramic manufacturing company or research institution where I can apply my skills and make a positive impact. Additionally, I aspire to give back to my community by sharing my knowledge and inspiring other individuals from disadvantaged backgrounds to pursue their dreams. Though I come from a poor family, I firmly believe that hard work, determination, and a genuine passion for what I do will help me overcome any obstacles and create a brighter future for myself and my loved ones.
Hi there, this is Adrian. So in my years of experience as a ceramic engineering student, I can say that it was a very amazing and memorable experience. Basically, ceramic engineering is a fascinating blend of science and artistry. We apply theories we learn in the ceramic material to the limitless possibilities of design. Ceramic engineering will allow you to explore your creative potential but also apply the power of technology.